Before I start with the next video, and by my count you've already watched 40 videos by the time you've got to this point in the course, I want to talk a little bit about this map that's in the background here. So this is a map of rainfall in inches across the conterminous United States, and rainfall seems like one of those continuous data sets, and so you would expect that to be a raster. But the way it looks like there are lines or maybe polygons for separate areas of the raster. So what the heck is going on there, do you think? Well, I'll tell you about making contour lines down the road a little ways, but you can imagine that this might be a raster map where the cells in the map each have a different value for precipitation or rainfall in inches. But in order to make it more visible in terms of different categories of precipitation, you could reclassify the raster, and that would be a local operation, and that's what I talked about in the last video, local operations. So you would go through and say, everything in my raster that has a value between 8 and 16, give it another new value, and then when you have the symbology for that new value, you make it this color, and then you reclass this range and this range and this range, and that way you're making classified raster data set. Okay, enough of that, moving on. Last time I talked about local raster analysis. Local scope is cell by cell. The answer only depends upon individual cells in one or more raster grids. Remember, there were 4 types of operations that we think about in raster: local, neighborhood, zonal, and global. This time I'm going to talk about neighborhood and zonal. Okay, so all these local operations we talked about last time, bunches of things you can do, and then you can use this raster calculator to combine or to make different local operations. So that's all local operations. Now we're going to talk about neighborhood operations. And just like with the vector model, the raster neighborhood type operations involve surrounding cells. So I'm going to make some type of computation associated with this focal cell. This is called the focal cell, and the answer that gets stored in the output is going to depend upon neighborhood cells. So here's an example where I have an input data set, and we'll say that the neighborhood is this 3 by 3 rectangle, and the answer that I'm going to store in the focal cell is going to be the maximum value in the entire neighborhood. In this case, it's 42. So when my neighborhood is over this area, the maximum number is 42, store it right there. When my neighborhood overlaps, let's say it goes out this way, then my focal cell is off the page. Here's when my neighborhood is like this. What's the maximum? The maximum is 30. So you can see how these things would work. You can have different shaped neighborhoods. The most common one is a rectangle. Sometimes people use circles and sometimes they use annulus. It all kind of depends upon what you're interested in doing in terms of the analysis question you're trying to answer. And you can even make a custom neighborhood if you want. But the standard default neighborhood is going to be a rectangle, 3 cells by 3 cells. There's 2 types of neighborhood operations. There are focal operations and block operations. A focal operation moves 1 cell at a time, and you can see that there's overlap between the neighborhoods of adjacent cells. So here's our first neighborhood, here's its focal cell. You move 1 cell over, and the first neighborhood is sharing common area with the second neighborhood. So that's a focal operation. A block operation doesn't have any overlap in neighborhoods. So it's going to make the neighborhood here, it's going to store the answer in all of the cells inside that neighborhood. And it's going to move the neighborhood all the way across, no overlapping. It's going to store the answer in all these cells. So that's a block operation. Here's another illustration of neighborhood. You can see the focal cell moving 1 cell at a time, and the neighborhood moves with it. And there are obviously overlaps between neighborhoods, between one focal cell and an adjacent cell. Here's an example of an operation called focal statistics. So here we have our neighborhood, and in the focal cell I'm going to store a statistical measure associated with the neighborhood, the average of all the cells in the neighborhood, 3.9, the maximum value, 9, and you can see how this works for all these other statistics. This shows you some of the syntax that you could use if you wanted to use the raster calculator to do this. You could say, Focal statistics, give it the name of the input raster, the type of neighborhood, this is going to be a rectangle, it's 3 by 3, and the statistic that you want, sum. And if you do that to this input raster, you're going to get an output raster that sums all the values in the neighborhood. So focal cell here, that's going to be a neighborhood that looks like this. If I add all the values together, I get 4. And you can see how it moves across one cell at a time. If you need to know more about how these things work, go to the help system. Block, statistics, block operations, focal statistics. Here's an example of block statistics. This one is going to be giving me the maximum value inside of the neighborhood, which is going to be a 3 by 3 rectangle. So if I look at this neighborhood, I see that the maximum value is 3. In a block operation, I store that output in all the cells of the neighborhood. The next neighborhood is going to have no overlap with the first neighborhood. Each cell in there is going to get the maximum value inside that neighborhood. This is one of the cases where if there's no data in your input neighborhood, it's not going to force no data in your output neighborhood. It's going to put the value of the maximum in the entire neighborhood. Filters. Filters are used generally to accentuate different aspects of a raster, or especially you have an image. So when you're doing image analysis, you do a lot of filtering. You have an input matrix, and you have a moving window, and from that you have an output filtered matrix. So here I have an example of a majority filter, and you can assume I have maybe a land cover map, and there's kind of some noisy things in this land cover map, and you can see this land cover might be beans, so this is all assumed to be beans, and there's very little chance that you're growing something else inside of that big field of beans. So you'd like to be able to filter out these kind of outliers, and so by using a filter you can filter out the outliers, and your result is kind of gets rid of that. So that's a majority filter. It's going to take the thing which has the most frequent number of occurrences within your neighborhood, and it's going to store that in there. There are several neighborhood operations that are associated with terrain. The 3 most important ones are slope, aspect, and curvature. I'll talk about these later when I talk a little bit about terrain analysis. Slope is, of course, the steepness of the terrain. The aspect is the direction that steepness is pointing or falling. And the curvature is whether it's curving up, curving down. That's actually what would be known as the derivative of the slope. Okay, let me look a little bit more at filtering. Filtering has to do with frequency, and frequency has to do with how quickly things are changing. So high frequency raster data set or an image has a lot of changes happening quickly. Low frequency has slow and few changes. So if we use a high frequency or a high pass filter, we're going to accentuate places in our data set where things are changing quickly. Likewise, with a low frequency or low pass filter, we're going to accentuate general trends. We're going to kind of smooth out things. So if there are spikes or noisiness in our data, we'll be able to use a low pass filter to kind of smooth out those things. So how does a filter work? You have your neighborhood, and you have an input raster, and you multiply the values in your neighborhood by what's called a kernel. And the kernel can assume different values depending upon what type of filtering you want to use. So in this case, if you look at the kernel, I'm going to multiply all my cells by 1/9. So this is the equivalent of averaging. So I'm basically going to make an average of all my cells, and I'm going to store that answer right there. So this would be an averaging filter. And that's the same as a low-pass filter. So it's going to smooth things out. If there are some high or low values in here, it's going to average those in with all the rest of the values. It'll smooth out those things. Here's another example. You can imagine maybe an image where there's an edge here, and there's another edge here. If I use a kernel that looks like this, I'm going to accentuate these vertical facing edges. If I use a kernel that looks like this, I'm going to accentuate the horizontally oriented edges. So you can accentuate different directions, and that's sometimes called a compass filter. This one has some noise in it, and when we use a kernel like this, what are we going to do? we're going to actually accentuate the noise. We're going to make a larger difference between the noise. We're going to give the center cell a much higher weight in the positive value, and all the other outlying cells as a negative value. So you can see in here that the output cells still have high values, but look at the differences between the numbers. Negative 718 versus positive 28. Positive 1000 versus positive 16. So you make the highs and the lows stick out more when you use this filter. Remember, when you do the filtering, you're multiplying your input by a number which is a kernel, and that number doesn't have any real physical information, so your output's not going to really have any physical information. It's just going to tell you where certain spatial features are, not what the values of those features are. Okay, there's a filter tool that you can use to do a lot of these filtering, at least a couple types. Low pass is going to smooth things out. Here we have a spike in our data. The low pass is going to basically average things, so it's going to smooth it out by taking that spike and smoothing it out around the neighborhood. What's a high pass going to do? It's going to accentuate places where things are changing. So here we have a block that's changing 5 to 9 inside this block. And here we go from minus 9.6 to plus 9.6. So we're going down and then up. We're accentuating that change. And again, no physical information in the output. Okay, you can do a whole bunch of different types of filters. An image analysis program will allow you to do a really good job at this, but ArcGIS has gotten a lot better at this over the years. These are the different filter types that you can use to make convolution filters. These are the two that you're going to be able to use just using the filter tool. If you want to do a different type of filter than are available through the filter tool, there's something called the image analysis window that you can open up inside of ArcMap, and that'll allow you to do different filters, and your filter types are down here. You can pick your filter types. Okay, the other type of raster operation I need to talk about in this video is zonal. That involves what you would expect, zones. So this graphic shows this being a zone. And so what we're going to do is we're going to do our calculations based on that shape. And all the cells that fall within that shape we'll do a calculation for. So it's kind of like a custom neighborhood that changes across the data set. A bunch of tools you can use again to do zonal operations. Here's a zone statistics. You have to have a raster that defines the zones. All values that are the same define a zone. So this would be zone 4 right here. I'm going to go in to my elevation raster and I'm going to compute some statistic based upon these cells that fall inside of zone 4. Okay, so all the cells in this zone are going to get the same output based upon the calculation that uses all the cells that fall in that zone. So here's the zonal minimum. If I look at this zone, I see the minimum value is 9, stored in all the cells. Zonal range in this zone goes from 9 to 10, so the range is 1. And you can see how that works for all of these statistics. There's a bunch more you can get, right? Sum, mean, standard deviation, variety, zonal areas. For zonal area, we only need, or perimeter and thickness, we only need that zone raster. We don't need a value raster because it's actually working on the geometry and not the values that are in it. So the area that's inside of this zone is the area of 4 cells. What does a zonal histogram do? This is a very useful one. Here we might have an input raster data set that has land use types. So let's just assume we've got blue here as water and we've got green as forest. When we do a zonal histogram using this land cover data set as our zones, we can apply that to an elevation or a slope data set. So we can say, within the water zone, what is the slope like? Within the forest zone, what is the slope like? And we'll get a histogram. And the histogram, in this case, you can see the example. In the water land use, this is the range of slopes in the water land use. Okay? So you can see that most of the slopes are really low elevation and low slope. In the forest, you have a big distribution, different distribution. Some of the forest is in the flats and some of the forest is in the very steep sides. So this will give you a histogram by land cover type. So you can take your raster data set, whatever it is, and you can kind of break it up by certain zones and get specific information broken up into zones. Tabulate area, again, you have a zone data set and you have some type of input data set, and what it does by zone is it looks at the values that are in the zone. Okay, so let's say my zone is the zone defined by zeros. So notice these aren't contiguous, they're separated to cells, but all the zeros are a single zone. How many values of 10 are in that zone? There's one value, there's another value, and there's another value. So there are 3 10s in that zone. There's one 11 in that zone. So where's the 11 in that zone? It's right here. There's one 12 in that zone. Here's the 12 that's in that zone. And there aren't any 13s in this zone. So you can see how this works. You get a table out that tells you by zone what the values are. Okay, back in vector model, we talked about the modifiable areal unit problem, and that was a problem associated with when you aggregate numbers to some higher level. So you aggregate population to the county or something like that. Well, you run into a similar problem with rasters when you're aggregating things by zone. So here we have a map, a raster map, without any districts in it. So it's just the entire map, and you can see we got some R's and some D's for Republicans and Democrats. If we draw the zones like this, the Democrats will rule because they will win most of the districts, right? Democrat majority, Democrat majority, Democrat majority. So 3-to-1, Democrats rule. If I draw my districts differently, the Republicans 2-2-2 will rule. So same raster data set, depending upon, in this case, our zones, will give us different answer. And if you do it in this way, it's going to be a tie because the districts are drawn so that nobody has a majority. That's called the zonation effect. Remember, that's like gerrymandering, where you change the shape of your zones. In this case, you're going to get different answers. The other effect that you can remember from this problem before is called the scale effect, and that has to do with how large the zones are. Larger zones are going to have less variation within them than smaller zones. Okay, that was quite a bit of stuff for neighborhood raster operations and zonal raster operations. I still have some kind of catch-all raster analysis operations that I'll talk about next time.